So my work is mostly on different aspects of weak memory models. Today I'm going to talk about it from a slightly different way, direction than the standard things. So I'll not be talking a lot about hardware or compiler optimizations, C model, things that program logics, but more from a verification point of view that is a bit unstudied in this community, I think. So the question that we ask ourselves is, there are all these well-studied verification problems under sequential consistency, and we try to understand what they mean. Are they still decidable? What are their complexity under weak memory? And this particular problem that I'll show was in my head for several years, actually. So I am happy I was happy to solve it in some solution in the end that I want to share with you. And is also the reason I think, even if you understand, you don't care about decidability, you don't care about semantics. So the way we approach this problem is develop an equivalent semantics to the original model and show decidability using the equivalent semantics. So I hope that the semantics itself is interesting. I think so. And if you care about decidability, then that's the only way to do decidability results for weak memory for a problem I'll formulate soon. That I know. So so this would be, if you know any other way to do it, I'd be happy to hear. So this talk is based on a paper from PLDI 2 years ago, and recently extended version in Tor Plus with more results. And so I was working hard and trying to explain the best I can in the Tor Plus paper. So if you want to see all the details, read there. So in the talk, I'll skip many things and try to give you some intuitions. And I have many slides, but I hope I'll not, for both of us, so I'll not have to reach to the end of these slides and show you the technical details. And feel free to interrupt, of course, with questions and discussions. So I try to make it active together also with the Zoom participants if we can make it. So the problem that we try to understand is the super classical problem of safety verification. Here is an example. We have a concurrent program. We have X and Y shared variables and also Z and local variables A and B. And we have these assertions in the middle. And all we want to know is whether the assertions are satisfied in every run of the program. So can we reach a state that doesn't satisfy the assertions? In this particular case, since this left thread is setting Z to 0 and the right thread is setting Z to 1, each of them is asserting immediately after that Z was not changed. So essentially, what we want to know is does this thing form a critical section? And it's very easy to see that yes, under sequential consistency, if the first thread runs first, it sets X to 1. And then the second thread will be stuck in this loop here. And if the second thread is running first, it sets Y to 1, so the first thread will be stuck in the loop here. So yes, so indeed it's not so live. It's not a good way to implement a critical section because there's no liveness guarantees. One of them gets stuck, but it is safe. Okay, so far? Cool. So if we now try to look at it a bit more generally, not just particular examples. So this problem is clearly decidable. I assume that the program has finite state in the sense that you have finite number of variables and finite number of values. Let's say only 0 and 1, nothing else. So the left thread, every thread can be represented as an automaton, as we see here. So the left automaton, the left transition system is a representation of the program that we saw before. Initial state, then this WX1 is the label that I want to write 1 to X. And then I'm stuck in this loop reading Y1 from Y for quite some time until at some point I read 0 from Y and I go on. So I don't have to go to all the details. And this red state is the bad state that we don't want to reach. And then you can also represent the other thread. And then you can take the interleaving of these two transition systems, which is easy to define. It's another big transition system, another big non-deterministic automaton, finite. And then you take the intersection with this thing that represents the sequentially consistent memory. It's just a state. The states of this is just the values of the memory, the map locations to values. And it has transitions. Let's say if you write 1 to X, you go to the relevant state. So it's a big transition system that represents the memory. So in order to see if this red state originally is reachable, you need to construct this system to see what is the red state here and here, what they mean in the big system, and see if you have reachability in this finite transition system. So it may look a bit big and complicated, but everything is one big finite state system. So decidability is completely clear. There's nothing interesting here. Yeah.
The edges that have big messes of things. What do they mean?
I mean that there are several transitions. So inside this state of memory, this is the state where x is 1, y is 0, and z is 0. You can do all these reads. So it's different arrows, self-loops.
Doing all these reads and writes simultaneously?
No. These are many arrows, many edges in the. Each of them, yes. Yeah.
Well, can you repeat the question for the online participants?
Oh yes. So they were asking if what is the meaning of this thing, and the answer is these are different loops. So I didn't draw them all, but there are 6 self loops from this state, each of them labeled with one of these chunks. Okay. So then this problem under sequential consistency is clearly decidable, and if you care about complexity, one can also show this is in the p-space complete. I'll not talk much about complexity. So in this analysis, we assume sequential consistency. If you never heard about shared memory semantics, so this is what you have in mind usually when you see a shared memory program, unless you are very special. The different threads, they take turns communicating with the memory. And so at every time there's one thread that is non-deterministically chosen and reading or writing from the memory. And this is a nice model, easy to understand, but unrealistic nowadays. There is no hardware that actually implements for like without special instructions sequential consistency. And we want to improve performance, scalability, fault tolerance of shared memories. So actually hardware these days provide weaker guarantees and better performance than this. And there is a lot of intuition, especially for the causal consistency model that I'm going to talk about today. A lot of intuition comes from a similar story in distributed systems, distributed data stores. So if you want to implement sequential consistency, essentially all the replicas in different places of the world, they have to agree after every step on what's the state of the memory. So it's very expensive. And same thing, we want to have weak consistency there in order to need less consensus in a sense. So a lot of my intuition is coming from this and not from hardware. But for this talk, these things are more or less similar. What do we know about the decidability of this classical verification problem when we now weaken sequential consistency? So we don't know a lot. There are a list of weak memory models that were proposed before, not so many results. So we know that for x86 TSO, this is the, I think, most studied weak memory model, the one by Intel machines. And we know that the problem is decidable. We know there is a power arm, we don't know much. We know about C11 model, that if this is a model that comes from software, that it leads to undecidable verification problem. So the question whether you can reach some state in a finite state program. The program is always finite. Because of the memory, this problem becomes undecidable. And in fact, this is even true for a fragment of C11, for release acquire fragment. If you know in C11, there are different levels, and one of them is this release acquire. I'll go more into the details when I need them. But even for that fragment, the verification problem is undecidable. And that is quite recent from PLDI 19. And there are many more models, but not many results like this. So specifically, this talk will be about causal consistency. Here I show it as just one model, but in fact, it's a family of models that is a bit weaker than x86 TSO, than the Intel machine, certainly weaker than sequential consistency. And the idea comes from distributed systems, from replicated data stores, and the intuition soon I'll try to together with you build a formal definition, a more formal definition, but the intuition is usually given like this: different nodes in the system, if you want to think about distributed system, nodes in the world, or if you want to think about the machine, different processors, different CPUs. they can disagree on the order of some events, on some operations, but they should all agree on what is called causally related operations. So we'll try to understand what it means if you haven't seen this model before, but this is one of the most classical models in distributed systems. So even for that, it was not clear what is the status of the decision problem.
I mentioned causally related is something that can vary.
Right. Yeah, it's a family of models. There are some different notions. I'll try to show the exact definitions to what I mean. But I use this term because it's more general than the one particular technical model.
Did I get this right? So, let me repeat the question.
Oh, sorry. What was the question? Whether causally consistent? What does causally related events mean? And it really depends on the exact model. Yes.
To clarify, you said causal consistency is weaker than x86 DSO?
Yes, causal consistency is weaker in the sense that it allows more behaviors than x86 DSO. Yes.
How does it relate to action like hardware, like ARM is going to be very weak? Is that covered by that?
Right. So ARM has even weaker instructions. So ARM has several instructions. Nowadays, ARM v. So the question was, how does it relate to existing hardware? And specifically about ARM, if you choose instructions that are strong enough to get causal consistency, you actually get TSO, you get x86. In Power, you have this something very close to causal consistency. You don't get x86 TSO. If you know the technical term is called non-multiple copy atomicity. This sometimes they use it. Never mind. But I have also one slide about this soon. So if we now go back to the example before, all these models, all these variations of causal consistency, they all agree that there is no causal order between X and Y, the right to X and the right to Y. They just happen in different threads, no knowledge about anything. In this case, the different threads can take different, they can think differently about the order these events happen. This is intuition. That's not the way I think about it, but some people think about it like that. And then you can read 0 and 0. Because left thread is thinking that X is written first, and right thread is thinking that Y was written first, and both see 0. And then you can get to violate the safety of this critical section. So it really depends on the model that we choose, whether some state is reachable or not. If you've seen the store buffer example, many weak memory talks start with that example, so it's exactly this one, this pattern. So is this a problem? Actually, when I was starting working on weak memory, I thought maybe you too, I don't know, this is too crazy, it cannot work in practice. This is just 0, 0, you break all this stuff. So how come airplanes don't crash? And by now, after several years, I have two answers. Well, the first one is more or less obvious. If you want sequential consistency in all these machines, all these systems, there is a way to demand it. It's not that you have to work with a weak model. You can always put some fence or something like this. But that's not where this talk goes. The other thing is actually more interesting. It's quite rare to find algorithms in practice that really need the full power of sequential consistency. Coming up with this example from before that is semi-realistic was very hard for me. It's not easy to find algorithms. If you take a book of concurrent algorithms, synchronization, implementation of locks, there are some. But most of them will be okay with causal consistency. That's just an empirical thought I have. I'm not a programmer, so I don't know how to justify it more than what is just my opinion. But this is my answer. How come things don't crash? Even if you don't have this in mind, usually you'll be okay. Okay, and in this form, there is no need to say something like we need to understand and define semantics. Sometimes it's not clear, but we cannot do verification if we don't understand the semantics. So let's be a bit more formal about the semantics. So the whole idea of causal consistency, and also the reason why, the way I understand it, why it is so good in so useful in programming, is in order to support this pattern that is called sometimes message passing. I call it flag-based synchronization. So let's look at this program. We have two shared variables, X and Y, both 0. First thread is writing to X1, to Y1, and then to X1. And the second thread is reading X and then reading Y. And this behavior that is annotated here, can I read 1 from X, know about the second right here, and Y, 0 from Y, I don't know about the first right there. And the answer is that in causal consistency in all the models, no matter which variation you take, this is disallowed. The whole point is to disallow this strange behavior. So this will never happen in these models. And this is super useful in programming, unlike previous example, like you usually initialize some data structure, do some stuff about the contents of some cells, and then switch some pointer or set some flag, and the other thread sees the pointer or sees the flag, and then it really wants to use the data structure because this is the way we pass information between ourselves. So this, if this won't work, then everything will break, my understanding. So causal consistency is trying to get this correct.
Maybe I'm misremembering, but I thought it's just in the summer school we just attended, gave an example where I know it's crazy, but where this could actually happen.
Right.
Is that possible? Are there some?
Right. So the question was whether this can actually happen. This is for Zoom people, and the answer is yes. If you go to weaker models like ARM, if you use the most primitive, it cannot happen on Intel, but if you use the most basic instructions, it will also reorder the reads, reorder the writes. Everything can happen there. You really need to be careful. But now we are not talking about a super weak model, but something relatively strong in this jungle. Thanks.
The causal consistency, if you have a causal order in a thread, then you maintain that. Is that
right?
One of the
yes. Yeah, this will be the next slide, so I'll not repeat this question, but I'll just reach it now. So now we want to make it formal, and this is where I wanted to switch to the iPad and try to do it with you, see what we reach. If we have, yeah, we still have time. Before I go to the verification question. So the model is defined what we call declaratively, sometimes people call it axiomatically, with execution graphs. It's not an operational machine, more or less. So let's try to switch, and you tell me if. So we would like to, should be enough space for me. We would like to talk about this program. X is, it was the opposite, right? Y is 1 was first? I don't remember.
Y was first.
Okay. And we want to understand if this behavior reading 1 and 0, is it allowed or not? So this kind of model, the way it is defined, it tells you construct the candidate execution graph, which looks more or less like this. You have a write y1 followed by write x1. So that's how execution graph look like. Read y, and now the particular example that we behavior that we care about, we want to know if y can read 1, followed by read x0. Let me know if I have some assumptions that you don't follow, but I'm kind of guessing that things should be intuitive. And then you also need the initialization that is implicit, that x is 0 and y is 0, and this is like before everything.
Yes, that is correct. Yes, you need to stop the read y and the read x.
Yeah, so A should be X.
But you're reading in the opposite y.
A should be x.
So the read y at the top.
Thank you.
The X and the A.
Thank you. There was...
Yeah.
Okay, now good. Okay, and now we need to, so that's how the graph looks like. There is the implicit initialization here on top that is before everything, writing 0. I assume that everything starts as 0. And now the model tells you, okay, this is all models do this. Every read has to be justified. You cannot just read out of nowhere. So you justify these reads, but what we call reads from edges. So the only way to justify this read 1 is from that right. And the only way to justify this one is from here. There is only one right of y0 in this graph. And now we need to check for what we call consistency. And this is where the models are different from each other. So causal consistency doesn't allow this, and I think it does it in a very natural way. The axiom that is going to be there, the constraint that is going to be there on graph. So let's try to glitch it together. Do you see what can be, what would be the violation in a sense that is happening here? What is violated? What important principle is violated that we would like to disallow? Anyone wants to play this game with me?
I can't see any causal loops, but I'm looking for causal loops.
You have a lot of intuition about causality. I don't. So what is bad? The thing that is bad is the read of y0, right? Until the read of y0, everything was okay. So why the read of y0, in a sense, cannot read 0?
Because it's written y.
Yeah, because there is this y1, but it's not just that it's there. It's
because you observe.
Yeah, it is observed not directly, but there is exactly. Thank you, Sam. It is observed via this path, and this is the causal relation for me. But it is observed via this path. So this kind of paths, we call them in causal model, happens before, and this is just these arrows and these arrows union transitive closure. Okay, so these paths, this happens before paths, and then the axiom would be you cannot have what color should I use? Oops. You cannot have a read of y from some right, obviously of y, provided that if there is another right of y in the middle. In what sense in the middle? In the sense that there is happens before path from here to here and from here to here. So this middle right, I was maybe it was exposing too much quickly, but that's the axiom I want to get. The middle right is overwriting the first right, whereby overwriting is again using happens before. It is happens before after. It happens after the first right, and the read is happens before the middle right happens before the read of y. So this shape here we need a read from edge. I mean RF, this green edge. This shape should never occur in our programs. So essentially, this is the basic idea of causal consistency and the way we define it in weak memory models. Now there are some tweaks, but this is the important case. This idea of I cannot read something if it is overwritten, and I know about the thing that overwrite it, and I know about an overwritten. They are all defined using some relations. The other thing I want to mention is that we also want to forbid crazy things like reading from the future, right? This is very bad. So we also require something very natural that this happens before relation is irreflexive, is actually a partial order, is not cannot have loops. So with that, I can go back to the.
The green arrows and the black arrows, what can you remind me of that?
The green arrow is called reads from, and the black arrow is program order. This comes from the program. Okay.
Can you give a quick intuition what weaker models left there?
Weaker models will not. There are several ways to do it, but they will not include all the program orders edges inside the happens before. They only talk about certain dependencies and things like that. But that's more or less. There are many tweaks you can do here. But yeah, I was trying to play this game, so this doesn't look completely artificial. When just now show you the thing, and we can go back here. Say, yeah.
So earlier we said that distributed nodes, in this case, would be different threads, have to agree on the constituent model. But that would mean that they have to agree on the program order. That's not the case. So what is the causal order here?
Program order is included. Causal order for me is this happens before, and program order is included in the causal order. So if
it's only program order on writes, then okay, so it's
only the order of writes is important, but not if there is a third thread. It also knows about these chains that can create by reads. So, but the program order on writes, I think it should be enough. No, not really. Let's take it later. I don't want to spend my whole time on just the model definition. That's why I'm. But I'm happy to talk about this later. So now, what should I do? Okay, so this is what we reach. This is the two axioms, the two disallowed patterns, and we go on with them. So far, so good. And this we support this example. Now there is and by the way, the result is that we allow this example to read 0 and 0. There is no problem. This is just because there is no happens before between this guy when it reads x is 0 it doesn't know anything about this guy. There is no happens before to this thread. So with just simple axiom that we had, we allow this 0, 0 thing. There is nothing that forbids it. I'll skip this one, but I maybe ask this question and leave it for later if we need it. We didn't say anything about concurrent writes. And this is exactly where the different variants, they kind of disagree. What happens in this program? When you have two different writes to the same log variable in parallel, x1 and x2, I guess, and there is a middle thread that is reading x repeatedly in a loop. In this case, since there is no, this guy doesn't override this guy, and this guy doesn't override this guy, we'll never violate our conditions from before. Right? The shape of this disallowed happens before thing happens before between two writes. But this program will never have happens before between the writes. So essentially our model of causal consistency so far is weak. It allows 1, 2, 1, 2, whatever I want. There is no restriction here whatsoever. So this is, if you know the technical terms, so it violates coherence. But for now, we can say we don't care. We can now add more things to the model if we do care. It really depends what model you want to achieve. Yeah.
Read from the package to the next one.
Yes, thank you, Yotam. So this is just a typo. There is only one read from to every read. As this edge, this error here is just a typo. Okay. So what can we do about concurrent writes? There are 3 different versions and 3 different technical terms for what you reach. One is to say, do nothing, just have what we have. It's actually good enough for many applications. And this is what we call weak release acquire. When people say causal consistency in distributed systems, it's not so clear which one they mean. So you need to be precise. Sometimes they mean this, sometimes this. Another way is to make sure that they are all totally ordered, to have another relation that orders the writes and use this one, and it's not that really happens before. And there you are 2 versions of this one that is called strong release acquire, and this one is called release acquire. And the terms release acquire, they come from C11. The C model wants to have this kind of accesses, and it did this choice. I'm not sure they really understood all these things when they did it, but they made the choice to go here. And I'll maybe say a few more words, but I don't want to go into all these small differences because they're not so important for this talk. But the few more words is in the next slide. I can also happy to share the slides with you. Essentially, this is the pattern we disallowed before. Now, in these 2 models, we also say that there should exist some other order on the rights. They call it modification order, coherence order, and it has some properties, different properties for different models. But I think I'll skip more the details of this for now. I'll skip also the examples showing the differences. So when I say causal consistency, there are actually 3 models that I know. Maybe there are more that are used introduced in the literature. This release acquire is the middle one. This is the one that C11 took, and also Java followed it. They have this inside the language. There is the weaker model. This is sometimes people call it CC, causal consistency. There is the stronger model. So if you use the power architecture and you require causal consistency with a particular way to do it, particular variables that will give you causal consistency, you get the stronger model, actually. And this is kind of sound and complete some result we had a few years ago. And what we know, okay, now back to verification. What we know about verification, we know that this is unfortunately undecidable. I don't know if fortunately or not, but we don't know anything. We didn't know anything about these 2. The reason I don't think it's so important is because we have this theorem. If you don't have right races, concurrent writes, and it's enough for this to assume the strong model, then all these semantics, they coincide. So most programs in the world don't have concurrent writes. Again, just empirical understanding I have. I don't know if it's completely true. And in this case, you don't need to understand anything besides what we already developed on the iPad. Yes?
So you mentioned that you use this intuition of distributed systems. They do have concurrent writes.
I use the intuition of distributed systems, but I claim this on programs and on shared memory programs in hardware.
Divergence there is, am I right? Or?
Yeah, I'm not sure. I don't know.
Well, I mean, intuitively, it seems like, I don't know, multiple people trying to
Take
the
this.
same flight or something. That happens
Yes.
all the time.
Yes, many of these examples are like that, but I made enough of bold claims before. Let me not make another one. Okay. So what we proved in this work that the verification problem both for S array and W array is decidable. So this undecidable thing is surrounded by two decidable things, and this means that array reals acquire is also decidable if you don't have these right races because of the right race freedom theorem from before. But what is, I think, more interesting, whether something is decidable or not, is the new semantics that we needed to develop in order to get this.
Is it decidable whether your program has these lists?
So this is a very good question, but the question was, is it decidable whether a program has these races? And this is where this theorem, you need to check races under S array. The strong model is enough to not have races under that one, and this is what we showed is decidable. So the answer is yes. Yeah.
In your example, there was two writes to Z, right?
Maybe.
Do you mean that in your example before? So are they concurrent or not? Either the race or no race?
It's not a race because it is a race there. Yeah, it is a race because you can read 0 and 0 and they happen. But if the critical section is correct, then it will not be a race. Okay, so what do we know about decidability? We actually know that this problem is going to be very hard in terms of complexity. It will have non-primitive recursive complexity. And this we know because the same thing happens on x86 TSO. We can simulate these lossy channel systems. These are the deterministic automata that communicate with a queue between them, and they write messages to queue. All finite alphabet, and the queue is lossy. If the queue is, in this case, this problem is non-primitive, it is decidable whether this system can reach some state, and it's non-primitive recursive. And we have a reduction. It's all followed from previous, so there's nothing much new here. So we don't hope to have a lot of good complexity, but we are still interested in the fundamental problem of decidability of this reachability in these models. So how can we do reachability? First, we would like to think about it as operational semantics. All the reachability approaches, they try to construct reachable states and things like that and increase the set of reachable states. So it's kind of hard to think about it with the declarative axiomatic semantics. But the observation is that there isn't much difference. If you think about the graph that you have at any point as your state, then essentially what you have is an operational semantics. Every step of the program adds one event to the graph. If it's a read, it also picks where to read from. And you go on adding event to the graph. So instead of having a memory, just a normal memory, my memory is the graph that was so far. And every time I need to satisfy the consistency constraints. So I can define operational semantics in this way, trivially. Not completely trivially, I need to check that the consistency condition is prefix closed. So consistency of this last thing implies consistency of the rest, and this is the case, but it's very easy to check in this case. So I can define operational semantics. If I have operational semantics, maybe I can use reachability. I can solve reachability in this operational semantics. What's the problem? Why is it different than sequential consistency? That also is some sort of operational semantics. Can someone see immediately the difference? So the difference is that even if the program is finite state, this system is infinite state. The graphs can be as large if you have a loop. The graph can be super large, like infinitely unboundedly large. And you have infinite states to check for reachability. You don't know how many iterations you need to be in the loop. Unlike sequential consistency, where the memory part was just a finite map. So we have these infinite state systems, and we need to check for reachability, and this is where the difficulty comes from.
Can you not use some model ideas like these old ideas of Macmillan, where you use a current sense and just run the other problem to a certain quantitative piece of behavior. And also in exploring reachability, you can take into account the concurrent action. So you instead of exploring this path and that path because they're kind of really different versions of the same thing, you can only explore one. Can you not use these kind of ideas here?
Yeah, I'm having troubles repeating the question, but the question was, can we use ideas coming from partial order reduction and model checking for this? So I think we can, and many people, including us, did it in other works, but it's also bounded, like without loops. You have first to unfold the loops until certain bound, and then you check reachability for this finite program that doesn't have loops, essentially. If you do have unrestricted loops, so you need a way to say that you did enough, and it's not clear how to do that.
I suppose in my own approach, he was unfolding as much as needed to, and push it a little bit, push the back.
Yeah, so how do you know that you terminate? For decidability, you need to give something that always terminates. So indeed, if there is another way to solve this problem, we'll be happy to know, but we tried this for a lot of time, nothing works, so I'm not sure it is possible. So, okay, this is what I said. Even if the program is finite, what happens in weak memory? Also the same thing in TSO. Why TSO is difficult for verification? Because we don't assume that the buffer, if you know TSO model, it has a buffer, we will not assume it has a fixed size. We say it can be arbitrarily large. So again, we have infinite state system. Here the infinity comes from the graphs here. So how can we attack this? How can we achieve decidability? And now we use the theory of well-structured transition systems. This is a theory to show decidability of infinite state systems, WSTS. And the idea, I'll try to give some intuition, not all the things inside, but the idea is that we need to find a way to represent our model as a well-structured transition system, because this framework is saying every well-structured transition system is leading to a decidable verification problem, decidable reachability problem. And the algorithm that we want to rely on, once we have this system, is something like this. It's super simple. We start with a bed state, S, and then in a loop, every time we calculate the previous states, pre of S, and we increase the set of everything that can reach the bed state. We increase, until at some point we reach a fixed point. And then in the end, we just need to check if there is an initial state that is also in these states that can reach a bed state. So this would mean that we have a violation. But this is not really an algorithm, because how do we know it terminates? And how do we represent this infinite set of states? This S thing can be infinite, it's not a finite set. Too quick or no? Okay. So what well-structured transition systems say, they actually find a way to make this algorithm an algorithm by saying we understand that we need a way to finally represent these sets, and we need a way to guarantee termination. And this is done with the same idea that we'll use this, equip our system with some well-quasi order. So it's a pre-order, like reflexive, transitive, with some conditions I don't know if I need all the conditions to tell you now. And the idea is that every set S in this kind, when you have this order, can be represented by the minimal elements of this set. So you have a finite generator for every set, and you can represent infinite set by talking about the minimal sets, the minimal generator. And this is order on the states of the system, right? It has nothing to do with the orders that we saw before. This is when you have two states of the system, you have an order. It should be a well-quasi order.
Can you say what it is?
Yeah, so it's a pre-order, reflexive and transitive. And the idea that every infinite sequence, A1, A2, A3, there should be at some point AI less than AJ. It's a bit more than well-founded order. So it's not that only there is no decreasing chain, it's also that there cannot be infinitely uncomparable things, right? So this is well-quasi order. And in order to be able to work with this representation, it won't work for every transition system. This well-quasi order that you find has to satisfy two properties. One property, this is the main, there are some others, but this is the main property, some sort of simulation relation. So whenever you have a transition from Q1 to Q2 in your system, and if you have a larger Q1 prime in the pre-order, there should exist a Q2 prime that you can take a sequence of transition from here, and this Q2 prime should be larger than Q2. So with this property by itself, you can show that it's enough to work with minimal states, and you can also show, because of the well quasi-order, that this thing has to terminate. So this is this framework is all about these definitions. Now, one observation is this one. If you have in your system a loose step, what is loose? You take your Q prime, I call it loose, I don't know if it's a common one. You have your Q prime and you go to a smaller state Q, and you can always take this transition. If you have this state, this kind of reduces you in the order, then you're all okay, because you get this for free. Never mind exactly how, but it's kind of immediate. If you have this step in your system, the dead one is free. So essentially what we look for is a lossy system, a lossy in the sense that you have this order on the states, and you can always lose information and go to a smaller state in your system. And if you can have such a system and define a memory like this, then you can use this framework for reachability. And this order has to be a well quasi order, otherwise there's nothing interesting to say. Right? If this is equality, let's say, there is nothing, we didn't get anything. So the challenge now is reduced after all this verification formalism to be able to show our shared memory system as a lossy system. There are two challenges for this system to be lossy system. One is that let's start from the second here, that if we actually lose something from the history, if we just take something from the history, I think about the order would be embedding of this graph one into another. If we just lose something, we'll allow more behaviors. It's not good. If we remove, in my example before, if we remove one of the rights, then the read can now read 0. It was important to have that right for not being able to read 0. So we cannot just remove things from the graph, from the history. It will create too much freedom for the system. You will not have an equivalent system. So just removing things naively will not work. And also the second thing is that partial order embedding, so embedding of this one into another, is not a well quasi order. Unfortunately, you can, with a finite alphabet, you can find infinitely many partial orders, and none of them is included in another, contained in another. I don't remember the solution to this exercise, but I think it should be that difficult. This is not the case for total orders. So Higman lemma is saying that if you have infinitely many words over a finite alphabet, one of these words would be subsequence of another at some point. And in trees or in orders, in partial orders, not trees is okay. In general partial orders, it's not the case anymore. So we cannot use this semantics for these two reasons, essentially. History is not lossy, and partial orders are not well quasi-order. So this is where we had a lot of time of thinking until we reached this key idea. I copied this from some psychology forum. Someone was asking, why do I keep focusing on the past instead of the future? And this is where the main idea I wanted to reach in the new semantics is that the new semantics will not remember the past. The past is not lossy. If I lose something from the past, I give myself more freedom in the future. But it will remember possible future. And possible future is, in a sense, lossy, because if I just remove something from the possible future, I restrict myself. I don't give myself more freedom. I restrict myself from what I can do. Now I'll show you some details, but that's the main idea. So we call it the potential of the thread. So every thread, instead of remembering all that happened so far, is going to remember the potential. What possible sequence of reads now I can do? At every step, I'll remember what reads I can do. Initially, I can only read 0. Someone is going to write 1. Now I can also read 1 at some point. So this is how some intuition looks like. It looks like this is from the point of view of one thread. So we have this initially, let's say this, not initially, but at some point we reach this potential. I can read 2 from X, then I can read 2 from Y, then I can read 0 from X, then I can read 0 from Y. Now I want to read from X, so I read 2. I kind of use this first thing from my potential and I remove it. This is how the semantics will look like. And then I can also read Y2, and remove this guy. And now there is this epsilon step. There is a internal loose non-deterministic steps in the system that just removes things without any read. So this can be just removed and so on. So more formally, our states will look like this. For every thread, we have a sequence of reads, possible values I can read. Initially, it's only 0. I can read 0 as many times as I want from every variable. And what is the order? The order of states is this one. So Q is less than Q pi. If for every thread, the potential of Q of this thread is a subsequence of the potential of the thread in Q pi. So this is subsequence. Subsequence is a well-quasi order, and the lifting to these finite maps. This assumes to be finite the number of threads is also a quasi order. So we are all set. Okay from this side.
These sequences that are finite.
Yes, thank you. So these sequences. The question was whether the sequences are finite, and yes, the star is the standard finite sequences.
What I might expect the program where the potential for reading, like read like any possible value might not, or might have an infinite sequence.
Right. We didn't consider infinite runs. The question was what happens with infinite runs, that I think, whether we can read infinitely time often the same value. We did consider infinite runs, but this particular case is not difficult. You can just say that a read does not have to consume this thing. We can still repeatedly read the same thing. Maybe we need some other tweaks.
Well, not the same thing. I mean, what happens if I just have a variable that I increment forever?
Right. If
reading the new value, I have stream values.
Yes. So that's okay because where was it? There will be a writer. Every time the writer is changing the potential. This was only reads, right? So there is a writer, and the writer adds things to the potentials of the other threads. It's not static. You have it from the beginning, and that's it. So in this example, how does it look like? Initially, the two threads. This is the example we saw. The two threads have the option to read. Okay, thank you. 0 and 0, and then this thread is reading. This thread is writing. Sorry, this right thread in the example I chose is writing 1 to y. So it puts in the second potential the option. Sorry, this thread is writing 1 to x. It puts in the second potential the option to read 1 from x, and the system goes on like this. Every write puts more potential. Every read consumes the potential. Now I'm out of time, but I'll tell you the next main idea where difficulty is once you reach this formalism. The main idea is so the read steps are now completely deterministic. And the write steps, they have to kind of predict the future and say who will want to read what and where, and put the right potential in the right places. And the question is, where can we put these things? If we just allow to put them everywhere we want, then this system will be too weak. If we say you only put them in the end, the system will be too strong. So we needed to find a condition to show essentially that these potentials can be maintained. They have enough information to be maintained. So I know the current potential, I take a right step, and I can calculate the potential after that step. So I'm out of time, but I'm happy to talk more about this. We had this later. We had this shared memory causality principle that captures this idea. It actually calculates. It's a long English sentence. I don't think you should read it now. It actually calculates the possible potential after the right step. That's the main idea. And there are more slides. The whole semantics is this, so it's not super complicated. It's just 4 rules. And there are some caveats. To conclude, let's say our results. So we proved that the potential system is equivalent to the original system, and we are not confident. So I did this one in Cork, and we showed them that we have a well-structured transition system, and from that we get decidability of the verification system. For the top model, we have something for this S array, and for W array we have another thing. That's it. And I have now an ad for positions in Tel Aviv if anyone knows someone. Thank you.
We have done one very quick question. Now we know it's decidable. Do we know anything about complexity?
Complexity is for this algorithm is super bad. It's non-primitive recursive. It's the worst complexity an algorithm can have, I think. So I don't go ahead and even though I suggested to have an implementation here, I don't go ahead and immediately do this thing. If what people usually do is closer to what Bilin was saying, the bounded model checking is the way to actually go and verify these programs, but in trust that it's enough to check some bound on the loops.